Hello everyone, I'm Eeshan Hasan, and today I'm going to be talking about improving medical image decision making by leveraging metacognitive processes and representational similarity. This is work done along with Jennifer Trueblood, Quentin Eichbaum, Adam Siegmiller, and Charles Stratton. The general structure of the talk will have three parts. In the first part, I'll introduce the problem, approach, and the data. Second part, I'll describe and apply the metacognition-based algorithms. And in the third part, I'll describe and apply the similarity-based aggregation algorithms. So, medical image decision making. Medical images are ubiquitous, and the interpretations of these images is important to the diagnosis of various diseases. But despite our best efforts, mistakes occur. One way to improve accuracy is to use second opinions. So, the first doctor might tell you that you think you may have cancer, but they're not too sure about it. You go ask the second doctor, and the second doctor tells you that I'm sure it's not cancer, and then you go back home happy. But this thing of aggregating decisions across people is studied in the wisdom of the crowds literature. So, can we use the wisdom of the crowds literature to improve medical image decision making? But there's a problem with second opinions. The first problem is that it's expensive and therefore it's rarely used in the US. And it's also rare. And therefore because there's a dearth of doctors in several parts of the world. So, can we use the decisions made by a single person and improve their accuracy? So the general way of aggregating decisions is to use wisdom of the crowd. So you've got different decision makers. Each of them gives their decisions. You combine all of them, take the more common decision, and that's your final decision. And this can be shown to improve accuracy. But in a phenomena called wisdom of the inner crowds, you can take only one decision maker and make them do the same decision, same task several times, and then aggregate these decisions. And it's been shown that under certain circumstances, this can actually improve the accuracy of that person. So the goal of the talk is to explore different methods of combining repeated decisions from the same person. The specific task that we're going to use in our experiment is cancer cell detection. So this is a stained image of a white blood cell. It's important to use these images to diagnose blood cancer. One can be asked, is this a blast cell or is this a cancerous cell? And this is the kind of stimuli that we use in our experiments. So in our experiments, participants had to decide whether a certain cell was blast or not blast, and then also indicate their confidence in their decision on a scale of 50 to 100. We used repeated decisions from the same person, and we wanted to see if using different methods to elicit different responses can actually improve the accuracy of our processes. Which is why in the first presentation, in one experiment, they were asked, "Is this a blast?" And in the second presentation, they were asked, "Is this a non-blast?" And the image was rotated as well. So this is called the dielectric bootstrapping and rotation manipulation. So in our experiments, we have experiment one, which use novice participants. In 1A, we actually do the manipulations to increase diversity. So in the first step, we ask, is this cancerous? And in the second step, we ask, is this not cancerous? Experiment 1B had the same question asked several times. There were 300 images on which these decisions were made, easy and hard images. In experiment 2 with experts, we have only 60 images, and it is similar to experiment 1A. So we have the manipulations to increase diversity. Um, and the number of expert participants that we finally used was lesser than novice participants. The use of novices is interesting for several reasons. The first reason is that it gives us a baseline to compare experts. The second thing is because all experts were novices at some point. So understanding novices tells us how we can train experts better. Thirdly, of theoretical importance is the fact that, and practical importance too, is the fact that they may have different decision making mechanisms. And finally, novices can be used to crowdsource decisions. First set of results show that both novices and experts do the task above chance. Experts are better than novices, but once again, we have to restrict experiment 1A to only expert stimuli to make this comparison because they actually had different stimuli sets. We look at the intra-rater agreement to see whether the manipulations to increase diversity of responses actually worked, and we check that between experiment 1A and 1B, there's a higher intra-rater agreement in experiment 1B, suggesting that um, our manipulations actually did work. So people gave more diverse or different responses in experiment 1A when we gave two different questions. Um, Experts were more consistent than novices in their decisions, which is again not surprising because they're more likely to give the same response. This is a quick result to show that the confidence manipulation sort of works and that correct responses, the red ones, are often higher than the incorrect responses, the wrong ones. So confidence predicts accuracy. Now for our metacognition based aggregation. So we first note that people have these metacognitive abilities, so they can make robust evaluations of their decisions. They're aware of their mistakes without feedback, and they can report confidence that correlate with objective performance. And we see this in our data, as I showed you before. So how do we combine with confidence? This is in Koriat 2012. He showed that if you have a pair of decision makers, you can combine them by taking the more confident decision maker. You can repeat the same process with the single person, which is what we're going to do, and take the more confident in the pair of responses. But it's important to note that because there are individual differences in the way people report confidence, you need to standardize confidence before taking it in your algorithm. So as for our results, we see that it works for experiment 1A. Accuracy goes up by something like 1.3%. Um, and this is across all the four cell types. We have a similar result for experiment 1B, where the accuracy does go up um, by a slightly smaller amount. So maybe it makes sense to get diverse responses. But basically, the important thing to note is that the metacognitive processes of novices can actually be used to improve their accuracy. Similarly, for experts, we notice that there's an improvement in performance, to something like a 2% improvement. So as a general summary, it works for everyone, novices and experts, and dialectic bootstrapping is not necessarily needed for it, but it might be useful. Now to the final part, the similarity-based aggregation algorithms. So within our stimuli set, we observe that certain cells are similar to each other. And now the question is, can we use this to aggregate responses? We originally had only two decisions on a given cell image. So what if we combine decisions from similar cells? So we've got this decision maker with these two responses. And then on this other similar cell, you've got another third response. And you can sort of keep looking at other similar cells and their decisions and get more and more decisions into the bag and then take the final algorithm. Now we have to finally see if this thing works. And before we test this out, we need to first answer these two questions. One, how do we know if two images are similar? We can't have experts tell us that. How many decisions should we use to aggregate? So for the first decision, for the first problem of similarity, we use neural networks. So the thing about neural networks is that they give us a representation that we can use to evaluate similarity. So the first representation that we use is the unsupervised representation. This is just a Google net trained on ImageNet. Here we just passed our images through this network and we looked at this penultimate layer as the representation. So two images with similar layer representations in this penultimate layer are probably similar images. So with supervised learning, we have a similar thing, just that the last few layers are trained specifically on cancer cell identification. So this actually picks up features that is relevant to this classification. So it has more information about the task at hand. So two representations, unsupervised and supervised. And it's this layer of the neural network that we're going to look at. So we can visualize these representations. So the crosses are blast and circles are non-blast. We notice that in the supervised representation, we have a clear segregation into blast and non-blast sections, but there is some amount of an overlap. But on the whole, most of the 96% of the closest neighbors belong to the same class. So it's a really good representation. The unsupervised representation, on the other hand, has little pockets of blast clusters and non-blast clusters. and 80% of the closest neighbors belong to the same class. So it's not as good, and there's a larger overlap. So our algorithm once again is to look at k decisions made on nearest neighbors and take the modal response as the final decision on that image. So we consider k is equal to 3 and k is equal to 7 because two decisions were on that image itself. Its closest neighbors are actually from that same image. So the third decision can only break a tie if these two decisions are different, because if they're the same, then the third decision can't really change it. And with k is equal to 7, we can actually override the original decisions made on that image. So to demonstrate how this might work, this is the decisions made by a single individual. The crosses are actually blast and circles are non-blast. The red crosses is where the person said it was blast and it actually was blast. And blue things points are where they said it was non-blast and it actually was non-blast. If you look at this region, this is a place where this person got it wrong consistently for a lot of images. So they said it was blast, but it was actually non-blast. So here similarity-based aggregation will not fix it because on that cell and the nearest images, that person made an incorrect response. Over here, on the other hand, this can be fixed by looking at the closest neighbors. So there are parts where this algorithm will fail and some parts where it will succeed. So as per our results, we observe that with the supervised representation compared to the average accuracy, we can actually see an improvement, a pretty significant 3% to 5% improvement. But with the unsupervised representation, we only notice an improvement in experiment 1A, which is significant. There's an improvement in experiment 1B, but it's insignificant. And with k is equal to 7, where you actually override decisions, it hurts performance. So basically, we can only use a good representation and we can only use a large number of decisions when we have a good representation. When we have a bad representation, we can't use as many decisions. Um, we notice that now with experts, it doesn't work. Now, this could have been because the experts were only using hard images. So we restricted novices to expert images and check it once again. And we notice that it works for the novice decisions restricted to the same set as experts. Um, and this sort of shows that similarity-based aggregation works for novices and not experts. And this might be because experts just give incorrect responses, um, and therefore we can't really expect them to um, incorrect responses on similar cells. So if they get a certain cell wrong, they'll also get the neighbors wrong, which is why similarity-based aggregation will not work, but it only works for novices. So as a summary, we observe that the quality of the representation matters. The quality of the representation interacts with the number of neighbors. So if you're using more decisions, it's more important for you to use a good quality representation. And finally, it works better with novices. It doesn't really work well with experts. And this might be because experts might be biased, whereas novices are noisy. So if you have noise, then this sort of a smudging process by looking at the neighbors can actually fix it. So on the whole, we explored different methods of improving um, accuracy, and we noticed that they work by and large, but where they work might be dependent on the decision processes that underlie those decisions. I hope you enjoyed the talk. Thank you.